Hi everybody, welcome to the Forces and Motion section for Unit 3, Area of Study 3. This would be the first part of that area of study. So let's just start off by saying that a lot of this will be dependent on what you've learnt in Year 11. So we're going to not rush through things, but move through things pretty quickly because it's sort of understood that you probably kind of already know what's going on if you've done Year 11 physics. If you don't, then that's a discussion that we need to have at another time. Anyway, let's start. So, just a quick recap of Newton's laws of motion. So we'll start with first law, which we'll just abbreviate with N1. It says an object either remains at rest or continues to move at a constant velocity unless acted upon by a non-zero net force. Okay, so basically what's going on here is you've got some object, all right? I'll just represent objects with a dot, and you can apply some forces to it. Okay, you can push it or pull it. That's basically all a force is, a push or a pull. The object doesn't care whether or not it's being pushed or pulled. All it cares about is, what is the size or the magnitude of the force that's acting on the object and in what direction. Okay, it doesn't have any other idea of where that force is coming from. It just knows that a force is being applied to it in some way. Okay, so the basic idea of Newton's first law is that you could be pushing or pulling the object towards the right with some force. Let's just call it 10 newtons. Okay, while at the same time somebody else could be pushing or pulling in the opposite direction with a force of 10 newtons. Okay, now these forces are equal but in opposite directions, so overall they're going to cancel out. Okay, so all the object experiences is zero net force. Okay, because one thing is pushing it from one side, another thing is pushing it from the other side. Both of those pushes are the same size, so overall the object doesn't experience any force. Okay, when this happens, the object will remain at a constant state of motion, whether that state of motion is at rest, where it's got zero velocity, or it could be at some other velocity, where it's moving, okay, but that velocity wouldn't change. Okay, however, if we just applied one force, say a push towards the right, then the object is experiencing an unbalanced net force, okay? The net force on this object would be 10 newtons to the right. So the object is going to want to move to the right. Okay, so if the object was stationary to begin with, it'd start moving, it'd change its motion, and start moving towards the right. If it was moving towards the left to begin with, it would now begin to slow down because you are applying a force towards the right that is causing the object to stop moving towards the left, or in other words, begin to slow down. Okay, so that's all the first law is saying. That's pretty self-explanatory. I don't think we need to go too much more into detail with that. Now the second law, this is the one that you probably use the most during your calculations. Okay, it says the sum of the forces acting on an object is equal to the mass of the object multiplied by its acceleration. Or in other words, F net equals ma. Okay. Now, one of the original formulations of this law stated that the acceleration that an object experiences is directly proportional to the net force applied to that object, and also inversely proportional to the mass of the object. So if we're using that original formulation, what we actually get is the acceleration is equal to the net force. Okay, it's directly proportional, which means basically it's equal to, while at the same time being inversely proportional to the mass. Okay, so in plain English, this basically just means that, if you push an object with more force, it's going to accelerate more quickly. Or if you apply a force to an object that has a small mass, that object will accelerate more quickly than if you apply the same force to a larger mass. Okay, the smaller the mass, the more easy it is for this object to accelerate. Okay. Another thing that's special about this relationship between net force, mass, and acceleration is that we can actually use this in terms of a system of objects, okay, where the net force, this part here, would be the net force applied to the system. So we can analyze and say, yep, each of these objects are experiencing a kind of force. We're going to add all these forces together overall for the system of objects. And that would be our net force. And the thing to keep in mind, though, is that this mass would then be the mass of all objects in the system, not just the mass of one particular object. Okay, we'll look at this more in depth when we answer some questions later on. But you've used this before. Again, we don't really have to go into too much detail, just a recap of your Newton's laws. Okay. Third law is, when one body exerts a force on a second, the second exerts an equal force on the first, but in the opposite direction. Okay, so basically, one way we can write this out is we can say that the force that object A applies on object B is equal to the force that B would apply back onto object A, just in the negative direction, in the opposite direction. Okay, so when you push on a wall, the wall pushes back on you. Okay, or if you pull a rope that's attached to the wall towards you, the wall is pulling that rope back towards it as well. Okay. This is probably one of the more misunderstood laws, and it's probably misapplied in a lot of situations. That's what we're going to get to in the next couple of slides. So, like I just said, action-reaction pairs can often be misattributed. Okay, so sometimes the normal force is misidentified as being the reaction to the gravitational force. Okay, and this is incorrect, even though both forces have the same magnitude. So here we've got a basketball sitting on a table. It's not moving, it's stationary. And we're going to look at the forces that are being applied onto this basketball. Okay, just look at the basketball. What forces is this basketball experiencing? Well, objects pretty much always experience a gravitational force. That's this blue arrow here pointing downwards. And because the object is not moving, because its motion isn't changing, it's got no acceleration, it must be that the net force is equal to 0. That is Newton's first law. Okay. Now, we have to have some other force that's counteracting the gravitational force, and you should recognize that this is going to be the normal force, the contact force between the ball and the table. So the table is actually pushing back up on the ball, so it stops it from accelerating downwards. Both of these forces are equal in magnitude, they point in opposite directions, so they must be an action-reaction pair, right? Well, that's where the misunderstanding is. Even though they're both equal in magnitude and point in opposite directions, they're not action-reaction pairs. This is not a Newton's third law situation, okay? So, what's going on? How do we look at this in terms of Newton's third law? Well, the force exerted on the ball by Earth's gravity should be paired with the force exerted on the Earth by the ball's gravity, okay? So that is Newton's third law. When one body exerts a force on a second, so when the Earth exerts its gravitational force on the ball, the second exerts an equal force on the first. So the ball exerts a gravitational force on the Earth, but in the opposite direction. So the ball would be pulling, here's the Earth down here, the ball would be pulling the Earth up towards it. And this arrow that I've just drawn should be equal in magnitude to this blue arrow that's being applied to the ball. Okay? And the reason why we don't sort of see the Earth moving around so much is because it's so big. Okay, and you can analyze that in terms of the second law, the acceleration that the Earth would experience due to this force that's being applied on it from the basketball. It's going to be very small because this mass in the second law is so big that this fraction becomes really, really small. So that's why we don't see the Earth accelerating all over the place when other objects are applying a gravitational force on it. Okay? So that explains the gravitational force. How do we explain the normal force? Well, again, the table itself is exerting this normal force on the basketball in an upwards direction. So that would also mean that the basketball exerts a normal force on the table in the downwards direction. Okay, so if we just look at the table itself, forget about the ball, the table at this point of contact here is experiencing a downwards normal force, a contact force, and that force should be equal to this green arrow here. Okay, those are action-reaction pairs. Okay, if we just look at the forces acting on the basketball, one of the forces is coming from the Earth, the blue gravitational force. The other force is coming from the table, this green normal force. So they can't possibly be action-reaction pairs because they're coming from different things. Okay, that doesn't make any sense according to the third law, which says one body exerts a force on a second. At the same time, that second body exerts the same force on the first. Okay, so that's not what's going on here with these two forces acting on the basketball. So just try and make sure you understand what that law is talking about. Doesn't pop up too much in terms of questions on exams and things like that, but it's still something that you really need to be careful with. Okay, and just as one final piece of information, a non-contact force cannot be paired with a contact force in reference to the third law. So the non-contact force, this gravitational force, the blue one here, that cannot possibly be paired with a contact force, which is the green one here, the normal force. Okay, so it just can't happen. If you, just think about it for a little bit. All right. Anyway, I'm going to stop there. So that's just a reintroduction to Newton's laws. We are mainly concerned with first and second law when we analyze force problems, which we'll do in the next video. All right, see you then.